Hi everyone! It's been a while since I uploaded my last video, but that's not because I'm lazy. Well, at least I hope so. Actually, I was busy thinking about circles. Everyone knows what a circle is, and I bet all of you have seen a lot of them in your lives. Circle is a spectacular shape, and it plays a huge role in mathematics. It can be defined in many ways, but this particular definition is my favorite one. We consider a point on a plane which we will call C, the center, and a certain positive real number, let's say r, the radius. Now we consider a point P such that the distance between P and C is equal to r. Set of all points with that property is called a circle. I like this definition a lot because it straight up shows what circle intuitively is: a set of points at a given distance from a given point. There is one more reason why I chose this definition as my favorite one. It gives you space to tweak it a little bit. For example, we don't need to choose one center point. Instead, you can choose two of them, C1 and C2, and seek points P for which sum of lengths of segments PC1 and PC2 is equal to the given radius r. By making this small change, we created a totally different yet similar shape, an ellipse. What's interesting is that we can choose any number of center points, let's say n points, to create a shape called an ellipse, and thus one ellipse is a circle and two ellipses is just an ellipse. People who work on optimization and computational geometry most surely know these shapes very well. Firstly, they were introduced in 1686 by a German mathematician Tschirnhaus, and they are sometimes called Tschirnhaus'sche Einkurven. In this article, n-ellipses are defined with irreducible polynomials, and it contains some further research and generalizations. And it has some cool pictures too. But let's not get too excited here. Before we can even talk about an ellipsis, we should firstly examine the normal two center points ellipse. Going further into this video will require some ellipse terminology, so let me quickly introduce it. As you remember, we defined ellipse with two center points C1 and C2. This naming might be a bit confusing, because neither of them is the real center of an ellipse. This point is. We will call these misleading ones foci, plural from focus, and from now we will denote them with the letter F. The line that goes through foci is called major axis, and the perpendicular one that goes through the center point is called minor axis. Distances between center point and these vertices are called semi-axis. The bigger one is the semi-major one. We denote its length with A, and the smaller one is the semi-minor one. We denote its length with B. Now we can formalize the definition from the beginning of this video. Let P be a point such that the sum of lengths of Pf1 and Pf2 is equal to 2a. Set of all such points create our beautiful ellipse. And yes, I mean it. Ellipses are truly beautiful, but also a little bit terrifying. For example, calculating circumference of a given shape might seem intuitively easier than calculating the area of the same shape. But in the case of an ellipse, it's quite opposite. Calculating area of an ellipse, it's pretty easy. It's just a simple integral, which then goes to pi times a times b. But the circumference, on the other hand, oh boy, the circumference used to be a real pain in the ass of a lot of mathematicians. And it still is. The integral that describes the circumference of an ellipse is, in general, not at all elementary. There is no simple formula for it, and all we can do is approximate it. Matt Parker made a great video on this topic, so check it out. And without further ado, let's dive deeper into the world of ellipses. There is one main reason I wanted to make this video: elliptical pool tables. In 2015, Numberphile shared a video about it, and I gotta say, I fell in love with it the moment I saw it. The way it works is that if we take any kind of ellipse, put a ball on a one focus and the pocket on the other one, then theoretically, wherever you hit the ball, it will rebound into the pocket. How cool is that? A lot of videos on this type of pull have been made, but none of the big ones prove why this works mathematically. The reason behind this magic is that any point on the ellipse itself makes the same angle to each focus. It's called focus-to-focus reflection property, and I'm here to finally prove it. Formally, this property means that if P is a point on an ellipse, then bisector of an angle f1, P, f2 is also a normal of our ellipse in point P, which means that in this point it is perpendicular to the tangent line. Therefore, we shall start our proof by taking any point P on our ellipse and bisecting the angle f1, P, f2 with line L1, and then drawing a perpendicular to L1 line which goes through point P. We will denote it with L2. Proving that L2 is tangent to our ellipse will conclude our proof. To do that, let's extend the F1P segment with a L3 line and also draw a L4 line which is parallel to L1 and goes through point F2. L4 intersects two lines, L2 at point Q and L3 at point F2 prime. Now we can notice that lengths of segments QF2 and QF2 prime are equal, which follows from the fact that triangles PQF2 and PQF2 prime have same angles and share one side, PQ. Therefore, if we take any point R other than P, which lies on the line L2, the lengths of segments RF2 and RF2 prime are also going to be equal. Because of that, sum of lengths of RF1 and RF2 is equal to the sum of lengths of RF1 and RF2 prime. And from the triangle inequality, it follows that this sum is greater than length of F1, F2 prime, which is equal to 2a. Hence, sum of lengths of RF1 and RF2 is greater than 2a, and this means that point R must lay outside of our ellipse. And this happens for any R other than P. So, by definition of tangent line, L2 must be tangent to our ellipse. Hence, the focus-to-focus property has been proved. This property that we just proved also uncovers another amazing fact about elliptical pool tables. If we put a white ball on some other place than the focus point, then the only way to hit it and rebound it into the pocket is to hit it along the line that connects the white ball's position and the focus point. Then, if we would hit the ball in the wrong direction and assume that it would bounce forever, it would never go into the pocket. But where will it go then? Well, we know that the white ball won't move outside the ellipse. That's how we defined its moves. But the real question is, what shape will white ball's path create? I'll let you figure that out yourself, while I'll be slowly moving out of sight. Thanks for watching. Bye.